All right, everyone. And continuing our data science track, we have a principal architect from Hortonworks. Please welcome Casey.
Wow, great crowd. Thanks a lot for coming out. This many data scientists in one room, you know, that's a lot of unicorns. It's really a lot of unicorns, all right? So my name's Casey Stella. I'm a principal architect at Hortonworks. I focus on data science, so I'm a working data scientist, I guess you would say. And I primarily focus on data science in using Hadoop, right? Because that's what we do at Hortonworks. We have a Hadoop distribution. So prior to this, I was doing data mining in the medical space, which you'll see a little bit in the demo as well. I was doing some signal processing in the oil industry, and I was a graduate student. But these days, I think a lot about data science, and I think a lot about doing data science. So that's what I'm going to talk about today. So one of the real big challenges here about data science is often I'll get dropped into places where I don't have either a deep knowledge of the domain or sufficiently deep enough knowledge of the subdomain that they want to answer data science problems in. So whenever I do these sorts of things, I'm often thrown into this sort of quandary where you have two options, right? You can either, you have to ask experts and spend time with experts. In medical, it's particularly difficult because that means spending time with doctors. Doctors are nice people, don't get me wrong. Some of my best friends are doctors, but they're extremely hard to get time with. And a lot of times, the answers that you get back are biased by their own experiences, right? A doctor has a small sample size, a relatively small sample size, depending on the doctor, right, and the subspecialty. Especially if you're looking for unexpected relationships in your data, right? If you just go by what doctors say, you're only going to get the expected relationships, right? They're coming at it with a bias. So I actually like looking at unsupervised machine learning techniques to do this, to help to find the organization in data. Like that's one of the things that I like to do the most because it helps me. I like building tools to help myself because I'm a selfish person. No, seriously, but I do like this. And data is extremely complex, right? As you all know. Especially medical data. And the more unstructured data, the more unstructured we get, the more complex the relationships get sometimes. Right. So right today, I'm going to talk about a technique that I used in the medical space, but I think it's broader than that. I think you can use this in a lot of different domains. So we're going to look at using unsupervised structured learning borrowed from natural language processing outside of the domain of textual data. So every time I say that, people look at me funny. It's like, you mean NLP techniques with non-text? That doesn't make any sense. That does not grok, right? Right. But it turns out a lot of these techniques actually do generalize. A lot of the work from Google in particular has been around, has not been forcing the structure of text in the models that they're using. You can see this most specifically with paragraph Tyvek. But word Tyvek also is the case, right? So word Tyvek is a vectorization model created by Google that attempts to learn relationships between words automatically, given a large corpus of sentences, right? So the input of this is the corpus of sentences. It's not the corpus and the part of speech, right? There's nothing inherently about the word necessarily outside of its position in the sentence, right? Okay, so it gives us a way to find similar words by finding nearest neighbors. Essentially, it's constructing a vector space with cosine similarity as the metric, right? Or pseudometric, whatever. Which is nice, because now I can do things like find similar words. It also gives us a vector space, so I can do things like algebra on those words. So I can say the vector representation of king minus the vector representation of male plus the vector representation of female is close to the vector representation for queen. So you can start playing these kind of, there is more structure there. You can do algebra on this space. Just a nice thing about vector spaces. Okay, so under the hood, it's using a neural network to learn. But the other part about being a working data scientist is I have to talk to people who are giving me money in order to do data science. And that means that they want to know what I'm doing and why it works. And that often means constructing intuitive explanations for what these things do and why that they might work. And if you just say, well, it's using a neural network under the hood, maybe a doctor would say, okay, but doctors are pretty skeptical, actually. They're fairly skeptical people. So it turns out some research by Pennington, Soker, and Manning showed that the word-to-vec model it's equivalent, it's a riff on word co-occurrence, right? Using, it's weighted based on window distance, right? Window distance being the distance, you're walking the sentence with a window, right? And lowering the dimension by matrix factorization, right? So they found an equivalent model. So it's essentially what the neural network is learning is this particular model, is what they showed. And I would suggest, there's a bibliography at the end of the talk. Look at the paper, it's really cool. Those guys at Stanford do a great job, and the guys at Google do a great job, right? So the takeaway here is that it boils down intuitively to a riff on word co-occurrence, which gave me what I needed to do to talk to the upper management and say, hey, this isn't actually that complicated. Okay, so what do I mean by non-textual data? Now you know the technique. Clinical encounters, when you go to a doctor, everyone's gone to a doctor here, at least when they were born, right? They may not remember it. Most people have gone to a doctor. So what a doctor does is they'll measure your vitals, right? Height, weight, BMI, or the nurses do that because they're the hardworking, they're the grease that makes the healthcare industry go forward. Labs are performed, blood is taken, you'll get your blood sugar taken or measured, stuff like that. And then finally procedures are performed. It's like examinations, maybe you'll get your arm set if it's broken, et cetera. Diagnoses are made for their internal records as well as for billing, right? They'll say that you have this disease or that disease or whatever. And then finally drugs are prescribed, right? So you can imagine this as being it has its own grammar, it has its own structure. You can't really prescribe the drugs before you know the diagnosis. You can't really have the diagnosis before you understand what exactly, before you take the observations, right? Like most events, this is a set of complex events with its own grammar, right? So each of these things can be considered words, and the encounter forms a clinical sentence. So the nice thing is clinical data is split up this way naturally, right? This is how we keep it. So it was very natural to start thinking about this in this term. In these terms. So we can use word2vec to investigate these connections between the clinical concepts. So what I really needed to do was whenever I construct features, I need to understand what diseases are similar to other diseases, what drugs are similar to other drugs. And this model, I hoped, allowed me to do that, right? So unfortunately, I can't show actual client data because of privacy rules, obviously. But there was a Kaggle competition where Practice Fusion, an EMR, an electronic medical records system, released some depersonalized clinical data, which is like super crazy, right? People never do that. So there's actually an open source depersonalized clinical data wandering around the internet. So 10,000 patients. So there's about 197,000 clinical sentences. So just to be clear, whenever I did this at a client, right, an insurance company, you're talking about millions of sentences, so a much richer data set. But 197 is actually quite a lot, right? So what we're going to do is or rather what has been done is it's been pre-processed in Pig and Hive, right? Because that's often how I find the data, right? People will put them in Hive, and then I'll use Pig to do some pre-processing, or maybe I'll use Spark to do pre-processing, and then finally I do a lot of the analysis in Spark, right? Okay, so we're gonna hop over here. So what we're gonna do is, this is a very small amount of code, right? So it turns out MLLib has a word2vec implementation, and it's had it for some time, which is quite nice. So I'm gonna create a vector space of 100 dimensions, and I'm gonna fit my sentences that I pre-processed. And I'm gonna have some nice helper methods here to take the diagnosis code. In the US, we just moved to ICD-10. We had ICD-9, that's where all this data is. So essentially ICD-9 is a diagnosis code ontology. So it has it's a coding scheme. So this code means this disease. right? So I'm gonna, instead of printing out a code, I'm gonna print out the description so you guys can see it, okay? Okay, so easy. So the first one we're gonna look at is heart disease, because I'm American and we're all dying of heart disease, turns out, right? So I figured that for my own self-preservation, I better get a handle on this. So one of the nice things about doing this kind of analysis is you have to figure out if it's right, or you build this unsupervised model, like you don't know if it's right. Like, what do you do? So what I decided, so you're back to the same problem. Do I start talking to doctors, or what do I do? Well, it turns out we've been actually doing a lot of medical research since, Hippocrates. So what we're going to do is we're going to look at some of the stuff that we do know. Can the model recover things that we already know about diseases? And can it recover things that we've just found out about diseases? And can it find some new stuff to look at, right? So heart disease is diagnosis code 440.0. It's atherosclerosis of the aorta. So your aorta is getting plaque in it, and that's bad. So the thing that pops up quite first is a personal history of peptic ulcers, right? Which is something that we've known about since the 1970s. You can see an editorial back in the 70s in the British Medical Journal discussing the connection between peptic ulcers and heart disease. So that's quite compelling. So one thing I should point out, this is cosine similarity. So these numbers are, the closer it is to 1, the closer it is to perfectly connected, right? So, that was very heartening for me as a data scientist looking at a model. It made me feel happy. And then I start looking down and I'm like, well, okay, neoplasm of the colon, all right, that may be connected. Hearing loss? Sensorineural hearing loss? That doesn't make any sense. Why would hearing loss be associated with heart disease? Well, it turns out in 2012, from the Journal of Atherosclerosis, sensorineural hearing loss seemed to be associated with vascular endothelial dysfunction and an increased cardiovascular risk. So what does this really mean? This means that what is the model actually doing? It's not finding causal relationships, and that's fine, right? I don't necessarily need it to find causal relationships. That's way too much for a model to actually be expected to do. What it is finding is correlations, and it's sifting through the correlations that are the most, that seem to be the most interesting to me, right? So it's recovering some stuff that we just found in 2012. The other one that I'll point out is knee joint replacement here. 0.9 is a fairly strong connection. Why is that the case? Is it just because, why would knee joint replacement be associated with atherosclerosis? Well, one associative connection would be age, right? So you're going to find a correlation between people who are old and people who have heart disease. But you also find that knee joint replacement in particular is quite common, and there's quite a solid a correlation between osteoarthritis, which will force you to have your knee joints replaced, and atherosclerosis in literature, right? So the other one I want to look at, so normally everyone, like the number 2 disease in the U.S. is diabetes, where it's, amongst the older population, there's a 20% prevalence rate for diabetes, type 2 diabetes, which is really, really bad. But one of the diseases that actually isn't as widely talked about is Crohn's disease, which is an inflammatory bowel disease, which is really, it's a terrible situation to have. The interesting thing is people don't, the reason why I wanted to look at it is people don't know why it exists. They know it's an inflammatory, there's some sort of immune response, right? But there's a lot of theories about why it exists, right? So you have people with Crohn's disease not eating bread and, the whole gluten-free movement in part. Right, so I wanted to look at that. What exactly are the factors around that? What's connected there? So the first thing that pops up relatively strong is arthritis, right? That's why in the world would Crohn's disease be associated with arthritis? Well, if you think about it, your immune system going crazy is going to start attacking your joints. That is effectively rheumatoid arthritis, right? So from the Crohn's Disease Foundation of America, arthritis or inflammation of the joints is the most common extraintestinal complication of Crohn's, essentially. So it may affect as many as 25% of the people with Crohn's disease. So there's a strong connection there. But one that isn't necessarily, wasn't even as obvious as that was these dental abscesses. That's an abscess inside of in your tooth. But why in the world would Crohn's disease be associated with dental abscesses? But if you think about it, so you'll notice I say a lot of if you think about it, because that's what the model does. It makes you if you think about it a lot, which is good for thinking about your data, which is good for being a data scientist. So your mouth is the first part of your alimentary canal, right? Your whole intestinal tract, all of that stuff is an existing system that starts right here, right, in your mouth. So it's not entirely unreasonable that dental abscesses or that diseases of the mouth might affect people with Crohn's. But one thing that we haven't found was actual literary. I didn't find anything in the literature connecting these two. But I did find a ton of things on the Crohn's disease patients' forums. Crohn's patients talk about this all the time. In fact, it's just given, right? When people ask about, I had this dental abscess, I keep having these teeth problems, I keep having these abscesses in my teeth, people will respond back and say, that's normal, no big deal. And they'll say, my doctor didn't mention this at all. It's like, well, that's just a part of life with Crohn's disease. Which is interesting. It pops up right here in the model. And the final one that I wanted to talk about was getting into the base reasons why this might exist. There was, so if you look at this, candidiasis of the skin and nails, that's yeast infections. That's a yeast infection of the hands, right? Or of the skin and nails. So keep in mind, ICD-9 is a very general diagnostic scheme or system, so it's rather vague. So I thought, why would yeast infections be connected? So there's a belief from the journal Critical Review of Microbiology that yeast infections are yeast. The body's inflammatory response or immune response to these kinds of infections are one of the reasons why Crohn's disease exists, right? So having these kinds of connections pop up in the model, this is something we found just recently, I think this was 2014, right, is very nice to show. So hopefully, I at least convinced myself that it was an interesting model. So for constructing features, instead of having to ask a doctor, I can ask the model. I can say, which diseases are connected? If I'm building a model on diabetes, I can find connected diseases and connected labs and connected drugs with diabetes. But I've only shown disease-to-disease connections. What you really want to find is what is sort of cross-system connections, like which drugs are most associated with which disease. Because if you ask a doctor, there's a ton of drugs, but everyone picks slightly different ones, right, often. Some are old and out of fashion, but that doesn't necessarily mean that they don't still get prescribed, things like that. So what you really want to know is, in your data, what does your data say is the most connected drugs associated with diseases, right? So we'll look at HIV, AIDS, right? Because I know that the triple cocktail is the most associated with HIV. If you have HIV, you'll be on some combination of this thing called a triple cocktail, right? Which is a set of drugs that will help fight HIV, essentially. So I looked at 042, which is HIV, and the first thing that came up was, in fact, the triple cocktail. So you'll find the connection isn't quite as strong as disease to disease, but it's still quite strong. So it shows that you can find these cross-disease, you can find these cross-type connections as well. So hopefully this kind of thing will help data scientists construct better models. Maybe help researchers point to connections and use their data to help direct their research. It's obviously not a replacement for scientific research, but it at least is perhaps a guide, right? And I think that this kind of setup is actually not unique to clinical data, right? A lot of event data and time series data have these kind of connections, this kind of inherent structure. So a lot of times we ignore those kind of, these sort of fuzzy structures or non-regular language type structures when we start looking at data because it's just so hard to parse. It's just so hard to find the connections. It's so hard to deal with. I think that techniques like this actually help that a lot. For this, I have about 10 minutes, and I want to stop for questions. And I'll point to the bibliography because you probably want to look these things up. So all the code here is on GitHub. All the code, the slides and everything are also on GitHub. They're here if anyone wants to see that later on. The bibliography is there. Any questions?
Thank you. Sorry for making you run. Closer, like that. All right. So, question I have is the word-to-fact model. How sensitive is that to the very local ordering within the sentences?
Yeah, so it's relatively sensitive. So it's sensitive as much as you want to ratchet the window size too, right? It's fairly sensitive, but thankfully most of these things are actually ordered fairly well. But you do point to a challenge, right? So a lot of these things happen in groups, right? Your labs are going to be grouped together, but not always. A lot of times in a medical situation, you'll have multiple diagnoses with labs. You'll have multiple events. You can think of it like a compound sentence, right? So it is somewhat sensitive. It's adjustable by adjusting window size. But yeah, it's something you have to be careful of. You have to actually look at the size of your sentence because what you don't want to do is have your sentences be only like 5 words long and have your window size be 5 because what that devolves into is just word co-occurrence, right? Which is actually interesting in and of itself and a very simple way to write that code, but you know, not picking out the complicated features of the grammar.
So, hello.
Hi.
I have a question about data because as far as we take ICD-10 classification, especially as some psychiatric illnesses are described in granularity, which is used in different ways when you take into consideration countries. So especially in Japan, many things are described as schizophrenia. However, in other countries, it is less, those are less specific fields of schizophrenia. And have you took into consideration the country from which patient came?
So that's a great question, by the way. So there's differences, and it's just to kind of recap and to rephrase. There are differences in how people code based on the country that you're in. In the U.S., up until like October, well, up until like the first of this month, actually, we used ICD-9, which is what this demo is based on, right? Which is a much less sensitive coding scheme. But in different countries, even with ICD-10, which is extremely nuanced, they code different ways. Right? The example was schizophrenia is coded very strongly in Japan, whereas in other places it's a more general code. Right? This technique is extremely data set specific, right? So if you start mixing country-wide data sets, they're going to code in different ways. Then that actually might be useful, and it might be interesting. But more than likely, you'll want different models for different coding schemes. And actually, in the United States, even in the United States, inside of individual states, they code differently. Like I've worked with insurance companies where certain hospitals have specific ways in which they code. There's kind of a general pattern, but there's definitely nuances there. And that is, looking at the differences between the models actually gives you some insight in the ways in which they code differently. And sometimes they code differently in bad ways, right? In inaccurate ways, both from a clinical perspective as well as from a, we want to make sure that we're coding things in a consistent way perspective so that our analytics all kind of match up. But yeah, I kind of dodged the question. I have not considered that. I have not considered that, but you should consider it. It's because it's only in the U.S. This data is only from the U.S. Any other questions?
Just wondering about
Yeah.
the dimensionality of the vectors you used and how you go about choosing that in the unsupervised space.
Yeah, so I went about it in a very unscientific way. I tried 300, 200, and then 100, and 100 worked better than 50, or 200 and 300. Unfortunately, that's the way it often is. There's not a great. So the idea being that the higher the dimension, the more nuance that you'll be able to find, right? But ultimately, this coding scheme is not a super nuanced coding scheme, right? So a super high dimension might not make a lot of sense. So 100 seemed to work okay. 50 was finding connections that were obviously wrong, that I could not verify with the data. So it's sort of iterative. That I have a mechanism to validate that the model is giving me back what I kind of expect. So I look at the coding scheme and I adjust the parameters so long as the model is giving me back things that I expect. So then I more trust the things that I don't expect from the model if I find a bunch of stuff that I do expect, right?
Great results, was very interesting, thank you. I was just wondering, did you look at or think about taking into account the hierarchical structure of ICD itself somehow, or is that just, does Work2Vec allow for adding some structure that is known, or?
So did I consider looking at what again? So
ICD-10, as far as I know, it has a hierarchical structure.
Oh, the hierarchical structure. No, I didn't. Though I will point out that Word2Vec is aimed at, that's one of the reasons why I chose Word2Vec. I did not specifically impose any sort of structure on it because if you think about words and how sentences are formed, there is that kind of similar structure, right, involved. It would be, what I would find interesting, however, is a lot of the work coming out of Stanford with Soker in particular and Manning is about integrating parse trees into their model, into their deep learning models, right? You'll see that in the sentiment analysis examples. Doing something like this, a riff on this, where you actually construct kind of a clinical parse tree is something that I am thinking about, and I think would be very interesting, because there's kind of this fight between the Google guys and the Stanford guys. The Stanford guys are like, you need to have a structure, you need to have a parse tree, and the Google guys are like, we don't need no parse tree, we got data, son, right? So, and there's kind of like a fight with the paragraph Tyvek implementations right now. And so Google came out and like, with their paragraph Tyvek implementation and like beat the Stanford guys, and now the Stanford guys have come back and beat the paragraph Tyvek's accuracy. So I do want to like play with this notion of a parse tree for this kind of data, because I think it's interesting.
I have two questions.
Yeah, sure.
One technical. You mentioned that you used 100 dimensions for dimensionality. What measure did you use to assess that? To assess the effectiveness? And
Oh, what? Yeah, sorry, go ahead. This is the second
Thanks.
question.
And second, I can see that this could really make a breakthrough in healthcare. So I'm wondering, what are the regulations across the countries to share healthcare data publicly?
Yeah, so the first one is, what metric did I use to validate my model, right? Is that the idea? So the metric inside the metric space is cosine similarity, if I'm misinterpreting that question. But the more interesting question, I think, is what you asked, which is, how did I know the model was right? And this is the problem with unsupervised models, right? You don't have, it's kind of hard to validate. My validation technique here was extremely ad hoc. It's, can I recover? I had a list of things that I believed were connections that humanity has determined as connections between the data, right? And when I tried different models, I ticked them off. You kind of build a unit test almost. You unit test your models, right? I have 27 seconds left, so I want to address the last question in that, which there's not enough time to address it. I do think that we need international models across for healthcare, and this kind of stuff would be a useful way to do that, right? To kind of, I think we should be building these kind of models on all of our data, rather than just trying to dig up Kaggle competitions that depersonalize data, right? I think these kinds of things help healthcare and help fundamental science. And I think we should be doing more of this kind of thing. I think we should not be quite so scared about losing our data, so we can all kind of advance at once. And that's my pitch for that. So sorry, I'm out of time. Appreciate the attendance.
Thank you, Casey.